Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we were talking on we'll continue our discussion on the driven nonlinear oscillators, and we saw that the equations are of the following form: x double prime plus omega by p x square x plus epsilon x cube is equal to cos s. And we see that the family of solutions are given by x of s comma epsilon. We are going to, again, the idea is our epsilon, since epsilon is not sitting at the term with the highest derivative, we will use the standard regular perturbation. And of course, when we do that, we cannot expect that the perturbative solutions, the components of the perturbative solutions are periodic. So we will have to introduce another variable s, which depends on the angular frequency omega, and again we can use a power series expansion of the angular frequency omega, and so on and so forth. So when we do that, this is all done in one of our previous examples. So we just quickly see what we have just mentioned by writing the form of the solution, and we see that suppose the driving force has period tau naught, right? And the family of solutions is x of s comma epsilon, has minimum given by tau equal to tau of epsilon, right? So tau, remember that tau is a continuous function, right? And it has to be, so on one end tau is a continuous function, right? Continuous function of epsilon, and also it is an integer multiple. It is an integer multiple of tau naught. So tau is tau naught, or 2 tau naught, or 3 tau naught, and so on. And both of these can only be possible when tau is equal to tau naught, which is a constant. So our period has to be a constant tau naught, and we can check quickly that tau naught is 2 pi here. And we see that when we start to write the regular perturbative solutions, the solution is of this form: x of s comma epsilon is x naught of s plus epsilon x1 of s plus epsilon square x2 of s, and so on. And we see that x naught double prime plus omega by p square x naught is cos of s. And once we check it, once we see that, this is the order epsilon to the power 0 solution, right? And we can quickly solve this. We find that the solution is of this form: x naught of s is p square by omega square minus p square cos of s, and plus, this is a particular solution because of the non-homogeneous right hand side, plus a cos omega s plus b sine omega s, right? And we see that omega is an integer multiple of pi. Omega has to be an integer multiple of p. If had it been the case, then we would have run into trouble. So omega is not an integer multiple of p. Because of this term here sitting. And what we have is that x naught has a period 2 pi. x naught has a period 2 pi, and we see that that is only possible when a and b both are 0, because here are two terms which has a period 2 pi by omega, and omega is not an integer multiple of p. So that is only possible that this solution has a period 2 pi if only this one term survives, that is cos s, right? And that brings us with the first solution. Now we can continue finding the next set of solutions, but I'm just going to write the final form. The final form of the problem, the solution is as follows. This is f naught by omega square minus p square times cos of pt minus 3p6 cos of pt by omega square minus p square whole cube plus we have that this is p6 cos of 3pt, and this is omega square minus p square times omega square minus 9p square, right? Okay, so, this is the following. So what have we got here? So this is the second one is the order epsilon term. The third one is order epsilon term square that we put it here, and that is going to end our discussion in terms of the solution to this driven nonlinear oscillator. Okay, so one thing I want to point out in this solution is that notice that there are terms containing frequencies which are greater than p, and hence this third term has period which is greater than 2 pi, right? And so we call this as the so-called superharmonic resonance, right? So what is p here? Right. So 3p is the superharmonic resonance terms, right? So we could also have, the moment we include higher order terms, order epsilon square terms, we will also have terms of the order of 5p, 7p, and so on, right? And that is purely this superharmonic resonance terms, and this is purely possible. This is possible because of the nonlinear term that we had in our equations. The moment this nonlinear term vanishes, right, or we take epsilon equal to 0, this superharmonic term, this completely vanishes, right? Even the higher order term vanishes. So the nonlinearity brings in the superharmonic resonance terms which has period greater than the driven period. Okay, so similarly we could have subharmonic response. I could quickly give an example without spending too much time. Here is a case of a subharmonic response. We see that the frequency for ranges of, here is one example: x double dot plus k times x dot plus x cube is equal to a cos t, and here my k is 0.04 and my a is 0.9, and one response has period 2. We will see that when we try and solve this problem, one response will have period 2 pi. I'm just stating the solution here. Readers can, viewers can quickly check my answer. So one response has period equal to 2 pi, and the other has period equal to 4 pi. So here omega is half. The frequency is half. Here frequency, the angular frequency comes out to be 1, right? So so we could have any form of a response, subharmonic, superharmonic in driven oscillators. and even chaotic motion is possible from a steady state in the presence of nonlinear damping terms. So nonlinearities can certainly bring on chaos. Uh, uh, so that is one another route to chaos. So then I'm going to shift my attention. I will now shift my attention from a single body dynamics or a single body phase plane analysis to a system of bodies or system of particles. And then we are going to generalize whatever we have learned so far, namely, for example, the momentum conservation, the various conservation principles, and the various laws of motion for a system of particles, right? And in the meanwhile, we will also see for such a system how does not only the external force or the internal force behave. What is the impact of the internal force or the interparticle forces on this system? Okay, so what we want is, what we are trying to show is the energy. We are going to start with the so-called energy conservation for multi-particle system. Okay, so the key concepts is that we have the key concepts we will cover are the so-called external and internal forces. So that is new to us this time, the internal forces, and the case of energy conservation. And what we have is we need to discuss some new set of coordinates to describe the system of particles. So let us start with some basic terminologies. We talk about configuration and degrees of freedom. So we consider a multi-particle system, right? Consider a multi-particle system, right? Of particles P1, P2, Pn, right? So the setup is as follows. So we have lots and lots of particles, and we are trying to find the eventual organization of the system of particles. So P1, P2, Pn, and so on. We call this system as S, and let us say the distance between any two particles is Rij. For example, P1 and P2 is R12, and so on, Rij, right? And this is my particle Pi. And what have we got is, these particles Pi's have masses Mi, Mi respectively, with position. They have masses Mi with position vectors R1, R2, Rn, and we see that this is equal to, given by the position vector Ri, right? So this is the configuration of the system. Now each position is specified by 3 coordinates. Each position Rij is specified by 3 coordinates in 3D. So we have that for n particles we will have 3n variables, right? It's a lot of variables to deal with. So from 3n variables we are going to reduce it to certain number of variables, the so-called generalized coordinates, and we'll see how. So the Ri's, this is the configuration. So we call this as the configuration of the system S, and each position is specified by 3 coordinates. So we have it implies that we have 3n variables to worry about. 3n variables to worry about, and what we have is 3n variables to worry about, and then so this is for system which is unconstrained, which means that every particle is free to move irrespective of the other particle. Now suppose we have constraints, then the number of variables are going to get reduced, right? So suppose so what I just said is, for a constrained system the number of unknowns are reduced. The number of unknowns are reduced, and we see that, for example, suppose we have 3 particle system, and let's say particle P1 and P2, let's say a 2 particle system P1 and P2, and let's say P1 and P2 are connected by a rigid rod of length A, right? And we see that in this case mod of R1 minus R2 comes out to be A. So P1 and P2 are connected by a rigid rod of length A. And then in this case, we have this constraint. This is going to reduce the number of unknowns from 6 to 5, right? Because this is one constraint. Suppose now we have the following setup. So this is example 1 here. Another example is, suppose we have the following setup. We have 2 particle system. Let's say P1 is allowed to move only horizontally, let's say along X, and P2 is allowed to move P2 is allowed to rotate, but it is connected to P1 with a light string, and the whole system is allowed to move vertically. The whole system is. So the setup is as follows. P1 is constrained to move horizontally. P1 is constrained to move horizontally, and the whole system moves vertically, right? So the whole system moves vertically, and only 2 scalars are allowed. So in this case, we only have the coordinates are mentioned completely by 2 variables, namely only 2 variables. The coordinates are only 2 variables, namely x and theta, right? So P1 is constrained to move horizontally, and the whole system is allowed to move vertically. So the only variables which completely define the system are this horizontal distance x and this angular displacement theta. So now unlike having 6 unknowns for the position for 2 particles, we now have only 2 unknowns, and hence we have the constraint system with reduced number of unknowns. So I call these unknowns as my degrees of freedom, or the variables which are undetermined, which are the degrees of freedom, right? So let me come to the definition of degrees of freedom. So before that, I should have also introduced the concept of generalized coordinate. These coordinates that I am defining, which are these new variables in which the system is completely defined, are the generalized coordinates. Okay. So what have we got? So degrees of freedom. So degrees of freedom is the number of generalized coordinates needed to specify the system. specify the system. Okay. And then the number of generalized coordinate needed to specify the configuration of the system, right? We need to write the entire sentence, configuration of the system, and then that is what is called as the degrees of freedom, DOF, right? So what we have is okay, fine. And degrees of freedom will be the number of variables, needed to define system motion. Number of variables needed to define system motion. And so that is what we have. Okay. So then what we see is, let us quickly look at some simple cases to figure out what do we mean by degrees of freedom, right? So example, the first example is find the degrees of freedom, find DOF of the first example is a simple pendulum moving in a vertical plane, right? So simple pendulum moving in a vertical plane, and we see that the only degree of freedom is theta, the angular displacement. So the degrees of freedom is 1. So similarly, how about a door swinging on the hinges, and we see that the door which is going to swing, again the angular displacement of the door is the only variable which is undetermined. So in this case also degrees of freedom is 1. And how about a soap bar needed to determine system motion. Soap bar needed to determine the system motion, and soap bar a soap bar sliding on a 2D hemispherical basin. That is what I wanted to write. Hold on. So a soap bar sliding on a 2D hemisphere, right? So typically our wash basin is a hemisphere, and a soap bar which is sliding will have 2 degrees of freedom, because a hemisphere on the surface we will have 2 degrees of freedom, namely phi, and we will have the theta angle. Hollow hemisphere is completely defined by 2 degrees of freedom. So here the degrees of freedom is 2, that is theta and phi. Okay. So finding degrees of freedom is quite straightforward, I hope. Now we will look at we talk about more about the energy of the system of particles, right? So what are we trying to say is, so let us look at the energy of the system, energy of a system of particles. So let S be a system of n particles, P, and we classify forces on S being external or internal, right? So of course the external forces are originating from outside the system, the internal forces are forces of mutual interaction. So external forces are originating from outside S, outside S, and example is gravity, and internal forces are due to mutual interaction. Okay. So let us now introduce some convention, variable convention, and so we call Fi to be external forces on any particle Pi. So I denote I with I. So these are forces acting on these individual particles Pi. Now let us call Gij to be the internal forces by Pi on Pj, right? And we expect that these forces, using Newton's third law, these forces are equal and opposite. So the internal forces by I on J is having an opposite sign with Gji, right? Because of the Newton's third law. So that is what is happening. Okay, so and also these internal forces must act. They must act along a line parallel to the straight line. Must act along a line parallel to the straight line, joining Pi and Pj, right? So Gij must be parallel to Ri minus Rj, and we see that so this is the direction of each of these internal forces. So we have two particles where the position vector between the two particles is denoted by Rij. So Gij acts either parallel to this direction or anti-parallel, depending on one or the other. Okay, so then we can write this Newton's second law for a system of particles. So the second law is mi times dvi dt is equal to fi plus summation gij, right? And then I can, so this is for each particle. I can now sum it up for all particles. So what we have is, let me call this, introduce this quantity T, which is half mi vi square. I take the speed, not the velocity, and we sum it up over all I. So this is my kinetic energy, right? If we differentiate the kinetic energy with respect to time, I see that I get that these two left hand sides are equal. So dt is equal to summation over all the external forces plus the summation over all the internal forces, Gij. Okay, and this is equal. Well, what I had to do was I had to take a dot product with Vi. So then this equation holds true. So this is this quantity times Vi. Okay. So so what we have is that on top of that, suppose a system, suppose this, we have this system of n particles. Suppose they move, do some work from time point A to time point B, then we can integrate these contribution of these forces from time Ta to time Tb, and we get the total work done due to this change in due to these forces. So the total work done. So suppose the system S in interval Ta to Tb, they move from A to B, right? So we have that Ta, so Tb minus Ta is summation I from 1 to n, and this is integral Ta to Tb Fi Vi and Fi Vi dt, right? And plus summation Ij integral Ta to Tb Gij dot Vi dt. So this is the net sum due to the due to the various forces from time point A to time point B. So then we have lots of results that we are going to start to prove from this point onwards, but I think I'm running out of time for this module. And in the next module, we will see the various forms of the energy of a system of particles and the various conservation principles, and also the specific cases when the forces are conservative and what happens to these energy forms in those specific cases. So thank you so far for listening. Thank you very much.